Hi, I'm Xingyi Wu from University of Pittsburgh. Today I'm going to talk about uniaxial strain effect on superconductivity in nanostructures at lanthanum aluminate strontium titanate interface. Before I start with the topic, I'd like to thank our collaborators both at University of Pittsburgh and University of Wisconsin-Madison and generous founders. Now let's begin. We work in the field of correlated nanoelectronics, which arises from two well-established fields. On the one side, we have the correlated electron physics, which is often studied in bulk materials and has shown superconducting properties. On the other side, we have semiconductor electronics, which allows us to have single electron control and thereby study the quantum system. At the interface of the two is interface heterostructure, which allows us to have both. We are interested in lanthanum aluminate strontium titanate heterostructures. It has been shown in 2004 that there is a high mobility 2D electron liquid at the interface. When the lanthanum aluminate layer is 4 unit cell, we can tune this interface to go through insulator to metal transition. In the system, people has also found superconductivity, magnetism, and tunable spin-orbit coupling. So these are all pretty interesting properties. Although in this talk, we will mainly focus on the superconductivity. It has been found in 2007 that this heterostructure undergoes a superconducting phase transition at around 200 millikelvin. The critical temperature can be controlled by electric field, and this field transition diagram has this dome shape. In the system, people have also found temperature and gate dependent superconducting gap. Now these features are similar to what's been seen in high transition temperature superconductors. There are many hypotheses in the superconducting mechanism. So one of them is ferroelastic domain hypothesis. It has been demonstrated by my colleague, former colleague, Pai et al., that electron-pairing and superconductivity exist at conductive channel edges, which is decorated by ferroelastic domain walls. To further explore why the heterostructure is a superconductor, we try to combine this material with our strain engineering techniques. Now, before I go ahead and talk about how we do the experiment, I'm going to review some of the studies on the strain effect on the superconducting transition temperature Tc of bulk strontium titanate. Early experiments observed decreases in critical temperature under hydrostatic pressure, while they saw both increases and decreases for compression along crystal 100 axis. There is a theoretical calculation which predicted a linear dependency on uniaxial and biaxial strain, which means that the transition temperature will decrease when the sample is compressed. It will increase when the sample is stretched. So there is an experiment where they observed a nearly 50% increase in critical temperature in niobium-doped strontium titanate under a tensile strain of 0.05%, which supports the linear dependency prediction that we just talked about. Now, we think that it would be appealing to see what would happen if we strain the lanthanum aluminate strontium titanate heterostructure, because that the superconducting system, it's at the interface, it might be it's two-dimensional for sure. And now let's talk about how we create those nanostructures at this interface. First, we have this piece of the sample that is naturally insulating. We make electrical contacts to the surface, to the interface, the electron gas. Then we use conductive atomic force microscope, c-AFM, lithography to pattern this interface. We take the conductive AFM tip, apply a positive voltage, and move it across the surface of the material. This will deposit protons and attract electrons, creating conductive channels. This process is reversible. We can apply negative voltage to the tip and erase the structures and create barriers. Now these nanostructures created can be as small as 2 nanometers, and they become superconducting at around 300 millikelvin. Now for the strand engineering, our experiment uses a strand cell, which is in the picture, that's manufactured by the reversibly. From the picture, you can also see our 5mm by 5mm sample, the square sample that's attached to 2 piezo stacks in the strand cell. So there it was actually attached by epoxy to 2 set of washers, where the washers were fastened to 2 piezo stacks. Now we create a 4-terminal nanowire device at room temperature, and then we do strand-dependent transport measurement at millikelvin temperature. That's 50 millikelvin, which is below superconducting transition temperature for the system without any strain. If we apply a positive strand voltage to the strand cell piezo stacks, the sample is under uniaxial tensile strain. On the other hand, when we apply a negative V strand voltage, the sample will be uniaxially compressed. We can calculate the strain from the displacement of the piezo stacks, which is measured by a built-in capacitor in the strand cell. Then, knowing the size of our sample and the washers, and then we also consider the location of our 4-terminal nanowire device, we can estimate the strain that's applied to the nanowires. Now here, for simplicity, we just use the displacement of the piezo stacks to divide it by the sample width, 5mm, and then we get a number, and we call this global strain. This page shows the result of our preliminary experiments. So it has a 4-terminal resistance of a 3 micrometer long nanowires. This is aligned with the uniaxial strand direction. We plot resistance as a function of current and strain. This data is taken when we continuously change the uniaxial strain from tensile to compressed. To see the features better, we plotted the y-line cuts of the intensity graph at some of the global strain values. We can see that the purple-colored regions, that is an indicator of zero resistance in superconducting state, and there are corresponding superconducting gap. And there are also some of the strand-induced not superconducting state. So we observe the smooth change in the superconducting critical temperature. Furthermore, we sweep the strand back and forth between tensile and compressed state, and we observe hysteresis. This page shows result when we sweep the strand continuously from compressed to tensile, and again we observe strand-induced not superconducting state. Now we talk about these data in the context of ferroelastic domain hypothesis. Strontium titanate undergoes a cubic 2 tetragonal ferroelastic antiferrodistortive transition at 105 K when the XYZ ferroelastic domains can form. It has been demonstrated that these conductive AFM lithography created nanowires They are elongated in z direction, ceding ferroelastic z domain after the transition. Now, outside of the conductive channels, there will be x or y domain. It has been shown that the superconductivity exists in the ferroelastic domain walls, decorating the conductive channel edges, so it might even be a one-dimensional superconducting system. Now, with our uniaxial strand cell, suppose the strand moves the ferroelastic domain walls. If the walls move away from the center, first towards the center, then the conductive z domains could collapse too much. Now, if the domain walls moves away from the center, the overlap with high electron density region will decreases, which can also destroy superconductivities. Now, these fits our preliminary experiment result when we saw destruction of superconductivity with uniaxial strand in both directions, whether it's compressed too much or stretched too much. Finally, we reached the end of the talk. I'm going to have a quick summary. We used c-AFM lithography to create nanowires at lanthanum luminate Strontium titanate interface. And under uniaxial and tensile compressive strain, we observed emergence of non-superconducting state at 50 millikelvin. And we also proposed the hypothesis that strand can move the ferroelastic domain boundaries and destroy superconductivity. This is a picture of my colleagues in Levy Lab at University of Pittsburgh. Thank you for your attention.